Colin, thanks very much indeed. That was very, 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 very convincing. I think you found yourself some support here. Good man. Anyway, can I throw the discussion open to questions for the second part, for the Quasar part?
Yeah, questions about Quasars.
So I kick things off. Actually, this is also a question for Peter. So I'm thinking about we're thinking about a rotating system. We have some rotating inertial thing. We're talking at some stage about 10 to the 12 solar masses.
That's for galaxies.
That's for the galaxy. Okay. So
yes.
So,
galaxies are not quasars. Galaxies are old quasars. Quasars grow into galaxies.
Good. Okay. We're talking about a 10 to the 7 solar mass object rotating, something of that order.
Yes.
So now what we have is we have a frame, and that frame is an inertial frame, which is now a rotating, through frame dragging, a rotating inertial frame.
Correct.
Now that stuff is rotating, as you say. I think it's a nonsense to think of this thing being a singularity and having angular momentum. So I think we really need to have something which is not black hole-like, which is extended. We're talking about frame dragging. We're talking about a rotational frame which is being dragged. So the local inertial frame is a rotating frame. Now, if one's thinking about a singularity, or even just something which is as small as a black hole, containing that amount of angular momentum for that kind of frame dragging to take place, it's not possible. The thing's too small, is it not? You need something which is much more extended to contain the angular momentum of the system, which is then, by hypothesis, dragging all of the things and creating the spiral arms and so forth. Would you agree with that statement, that the object which is carrying the angular momentum has to be quite, although very large in mass, has to be quite extended in space?
Well, no. The frame dragging drops off at 1/r. It is a distant effect, but if you've got a small mass, then the amount of frame dragging is small until you're very close to it. When 1/r it gets large, you get the big effect close to it. That's common sense, isn't it?
It is. The frame dragging is coming from a mass which is rotating. It's coming from an angular momentum of a rotating object.
No, it's not coming from the angular momentum. It's coming from the rotation of it. You mustn't think in terms of angular momentum.
Righty-ho. So
it's the rotation that's doing it.
Okay, I'll need to think
about it. It's Mach's principle in action. It's rotating. It makes things look rotating with it. It screws up what things look like.
Right.
You get funny forces.
You have a rotation which is not associated with an angular momentum then?
That's correct. Yes, don't think of it in terms of angular momentum.
Right.
The angular momentum is screwing stuff up nicely. Angular momentum would screw up the theory of black holes if it could, but the black holes have learned to rotate and to cancel it out.
I see. I mean, quite a lot.
They're alive, man. They're living off. They're eating. They're eating. They're growing.
Okay, right. I can see I've got quite a bit to learn here. But Peter, I wanted to ask, in terms of dark energy, could this be a rotating piece of dark energy that's sitting there, dark mass energy that's sitting there? Is that the kind of thing you're looking at when you're thinking here in terms of Sciama's principles?
I think dark energy is it's like a centrifugal force. But Sciama does it for the universe. He doesn't do it for a local system. It doesn't do it for a rotating local system, as you know, you're doing with these quasars and other objects. You're doing it for local systems. But Sciama's is for the observable universe. So
yeah,
it's a centrifugal force type effect. But it's whether you can consider that rotation or not, I don't know. But
I can see there's an interesting field of thinking here in terms of looking more locally at something.
I think a lot of people, me to some extent, think that we're living in a black hole, and I'm very interested in correcting.
How would we know?
Well, okay, but when you mentioned that when one is part of the rotation, one doesn't see or feel the angular momentum. Did I catch that correct? And that
Correct.
Okay, so that means that if we were on the inside of a black hole, it could be rotating, it could be doing all this stuff, but we wouldn't notice it. Is that what you're saying?
Well, the biggest black hole around here is the real center of the universe, probably 10 to 11, 10 to 12 solar masses at about 100,000 light years away. And that has quite a significant effect. We can feel that, I'm sure.
All right. Well, okay. I still have to get to grasp this idea of looking into something versus looking out to something. It seems to me that there's some fundamental change. And when you say that if I were part of the rotating system, the rotating thing, then these effects would go away. That is, I like that, but I'm not sure I believe it. So that's all. Just comment.
That's what inertia means. That's what an inertial frame is.
Can I ask one question about the being inside? Even if we think we're inside the system, we cannot see it. However, most of our observations are based upon optical phenomena. That we're seeing the radiation which is coming, light which is being emitted, we are measuring those things, we're measuring the Doppler effects and so on and so forth. And if they are coming from the different parts of the same rotating system, we should be sensitive to those changes because we are still seeing a part of us is still rotating, right? But even if I'm a part of a black hole, even if I want to pretend, and I'm not seeing the other part rotating, simply because of the Doppler shifts or observation effects would make us sensitive to those changes. Am I correct in thinking like that?
I'm sorry, you broke up several times and I didn't really get the gist.
And what I'm saying, simply because we are inside a rotating frame,
yes,
a rotating system, does not make us totally immune to the fact the other parts of the system are also rotating and the observations are based upon the emissions.
Yes.
That the other parts are sending us. So because of that, would still be sensitive to the rotation.
Yes, I think so. I can't.
I hope I didn't.
I haven't really got the whole picture. Sorry.
Yeah, I would have thought that. Okay, so
I'm still confused about the idea that your idea of an inertial rotating frame. We have to realize, what John said is that all these things have an extension. Now, if I'm part of an extended rotating thing, wouldn't I feel it? I mean, can you just...
That's it, yeah.
We are part of it.
You wouldn't observe it. You wouldn't feel it, but you should be able to observe it. What Carrie was saying is correct. If you look at photons coming in, if we're sitting in an inertial frame, which is now a rotating inertial frame. So we're actually in an inertial frame. That frame is being frame dragged by our local galaxy, which means that we're rotating at a constant velocity. We should be able, because if you think about a photon coming in, that photon is changing inertial frame as it comes in. So one should be able to observe that in terms of redshift of things forwards and backwards. So it could be, for example, the blue shift of Andromeda, maybe nothing more than the fact that we have to be rotating towards Andromeda at the moment, and it's falling into a rotating frame. Also, coming back to your original question about the rotation, what you have is, just imagine these things being vortices in a liquid. Now, the liquid is the liquid of space-time now, but imagine you have a lot of vortices. Those vortices are all rotating, but if you think about the interface between those rotating vortex systems, so intergalactic distances, those rotations are cancelling at some point. Well, they have to. On average, they'll cancel over large distances. But also, in particular, if two things are rotating in the same direction, that rotation is going one way to one and the other way to the other, even if they have the same rotation. So, but you should be able to see those effects. They're quite big effects, quite big velocities. You should see them in spectroscopy. The question is, have they been? I think that's part of what Carrie was saying. So I'm imagining this as a variation of frame as you move. So I think what you're thinking, Wolf, is spot on. You're right. It's confusing. And I think what you should be able to do is you should be able to see these things if there are these vortices. I could be wrong there because it might be the light is also in free fall, but that should change.
Well, I really like this. I like that image of a vortices inside of a larger liquid. That's a great image. But now, if the whole thing is rotating, should we not? I mean, are we saying these photons are dragged along so we never see a shift in them due to the overall rotation of our universe, if you will?
I think what needs to happen is you need to think, here's my ruler, this is my ruler, my local ruler. If my local frame is rotating, that ruler is rotating with the frame, or it's moving with the frame. So all of those rotations.
Right, but there's a force on it. There's a force on it if it's extended. It only goes away if you assume a point particle.
No, it's force-free, Wolf. It's force-free because it's all local. So what you have is you're always in free fall, so it's always a local effect. So look, this ruler's bending. But if I was ruler man sitting inside the ruler, I wouldn't be able to notice that ruler was bending. So if you like, that's the bending of space-time that's happening there. But if you were stuck in as a two-dimensional ruler man sitting in that ruler, you wouldn't know that it was doing all of this bending and twisting. But on the other hand, if you're looking at things coming outside of your ruler from another man's ruler frame, from another ruler frame, you should be able to see that. But locally, no, there's no force. It's force-free motion. That's what an inertial frame is. It's free fall. It's everything local to you is being modified by that. But it should be observable, I think. I'll need to think about it, but I think what Cherry was getting at was correct, that it should be observable. But Colin,
listen, guys.
This is fantastic.
Let me give you some information. The center of our galaxy, the real center of our galaxy is rotating 1 radian every 60 years. So it's not a big effect. You're not seeing a huge rotation. And light's traveling so fast, you don't see the effect of that on a light path.
Yeah,
but rotating, there's a lot of angular momentum there.
Yeah, it is. Okay, coming to
but it's,
as well. No, I love what you're saying.
It's very slow.
Well, it's just slow in radians per second, true, but it's not slow in meters per second.
No, it's big. We're talking about, well, you know what that is, because that's the rotation curve, and that's 300 kilometers a second.
That's quite a lot. Big. That's quite big. Yeah. You should be able to see it. You should be able to observe that.
Well, you can see it. You see it everywhere. Everywhere you look, you see galaxies rotating at 300 kilometers a second. You just see them everywhere.
Yes.
And it's not new. We've known they're rotating for years. We just haven't had a proper theory for it.
Okay, I see what you're saying. Right. Yeah, and maybe it is a slow rotation. Yeah, you're right. Okay, good. Yeah, good. Fascinating stuff.
Could I ask you about the Lyman Alpha Forest?
Yes.
I mean, I was a fan of art, I must admit his observations were good. But the one I see with these huge redshifts being intrinsic due to the quasar itself, that when you look at the light from the quasars, it's littered with Lyman Alpha lines.
Yes, I know.
Where the light passes through a hydrogen cloud, it absorbs a certain frequency that gets redshift and so on. And these lines can be traced right back. They don't quite go to the redshift of the actual quasar. The idea being it's fully ionized around the quasar, there's no hydrogen atoms there. We've got these lines up to at least a redshift of 4, some of these Lyman Alphas lines are done. To me, that means that the quasar must be at the redshift given, or any intrinsic redshift must have a mechanism of putting these Lyman Alpha lines in the light from it. How do we explain these Lyman Alpha lines in the light from distant quasars?
Well, I've spent some time on that in the book. Actually, it's just the rotating clouds around the quasar that are causing it. You said it a few minutes ago. You've got clouds of hydrogen absorbing and re-emitting. You get these Lyman Alpha lines from all the way from the full redshift of the quasar all the way out.
All the way to us?
Well, not all the way to us. All the way for a while, anyway.
They get quite close.
Yes.
They
You
get
get
very
right up to the black hole. You get almost right up to the black hole, yes. Yeah.
Okay.
Okay.
May I suggest, Lyndon, would you have another group you talk to of astronomers and astrophysicists?
Yeah.
Is that a group that Colin should be talking to?
I don't. Well, we do it privately. I'm talking to a guy who's at Imperial, and he's been looking at quasars. And I probably mentioned that he's just sent me a paper which he's got, and he was looking for this arch redshift. His conclusion was total shock to him when he found out that the evidence was there was an intrinsic blue shift in them. But that's just another one there. I mean, the other thoughts are you've got quasars and fast radio bursts. If I remember rightly, one of our problems is saying that these are so immensely bright, these quasars, they can't possibly be at that distance. But the problem, and there's, again, fast radio bursts are so incredible energetic. Well, that's because you're, I mean, one answer to that is you're assuming that the object's emitting light in all directions. You imagine being out at sea and a searchlight from a lighthouse hits you, you work out the intensity, then, and then if you assume it's giving that light out in all directions, then you think, wow, that's incredibly bright. This is, I don't believe in aliens, but this is why people say these are aliens sending, because these signals are beamed towards us. Could it be a natural effect that somehow the quasars aren't giving the light out in all directions, but it's being beamed in a certain direction towards us?
Don't know. This is standard theory, and I don't believe it. I think most quasars are spherically symmetric, and they're much closer to us. And the reason we think they're so bright is because we think they're at the distance given by their redshift. The redshift is due to the gravitational field of the black hole. And they're not at that distance. They're much, much closer. Look at that graphic again, the one I gave you at NGC 7603, I think. And those quasars are not at the distance they appear to be. Much closer.
Well, I find it hard to believe. I mean, we'll agree to disagree, but with the Lyman alpha forest going up to redshift of 4, and then the quasars are slightly more than that, it seems to me maybe they are that.
Well, what's that got to do with it? They can be quite close. The gravitational redshift will cause the Lyman alpha forest to exhibit that redshift. The clouds that are doing it are subject to gravitation from the black hole.
We'll agree to disagree on that one, Colin.
Well, have a look. Have a look at what I've written in the book. I've written about the Lyman alpha forest. It's in there. It's in the index.
That's good. I think we all want to have a look at this book now. Colin, can I ask you about something? Just the power source for quasars. Do you have any opinion on what's powering quasars? What's actually going on in terms of quasars?
It's accretion. It's accretion. The energy from accretion, gravitational energy. Things are falling in, and they're giving off their gravitational energy. Only a proportion of it comes out. If you look at the model, the spherically symmetrical model that we described, it's all in great detail, and you've got the amount of energy coming off, and everything's there. And it fits. It fits all the observations. What it doesn't fit is if you assume that they're at cosmological distances.
Okay.
And it's not until I found that that quasars could absorb angular momentum, could just change it so that the spherically symmetrical model works, that I realized what was going on.
Okay, I should say I have a different view about what might be powering quasars, and does remind me of something. If you remember, people were worried about what was powering the sun at the interface between the 19th and the 20th century, and one of the ideas was that it might be coming from accretion, from bombardment of meteors coming in and gravitational. That was one, and the other one, coal, of course, before nuclear power was discovered. So it's quite amusing reading some of the old articles on that, but I'm not sure I buy accretion, at least not to the kind of cosmological distance that art would suggest they were. And by the way, I must say I've been a fan of art ever since I learned about them 20 odd years ago. And anything you can do to, and it is an absolute scandal what was done to ARP, I completely agree. And anything done to restore that reputation is a very, very good thing in my view. So, but anyway, it could be accretion. Okay, good.
Actually, I don't know whether I could quickly find the graphic that shows that. Right. Now, can you see this wonderful picture?
Yes.
The Kobe satellite picture. That's our galaxy seen from the Kobe satellite. And as you can see, it looks as though most of the stuff that is coming is from one side of us. So we're out in the dark region. Okay. Now, when they put this graphic up, they assumed that Sagittarius A star was at the center of the galaxy. So the axes go through Sagittarius A star. Now I put the axes up here somewhere. Here we are. Here are the axes. I did this very, very carefully. I haven't fudged. Those are the axes for this Mollweider presentation. Those are the axes. Okay. But if you look, they don't go through the center. And there's the bulge. Well, there's a bright bit, but there's also the bulge. And I put the ring round the big bit of the bulge. But anyway, maybe it's over here somewhere. But even so, it's not at the center here. Sagittarius A star is not at the center of the galaxy. It's slightly up and it's slightly to the right. And so that corresponds to quite a big distance. So
you're talking about that being the mass center.
No, I'm talking about Sagittarius A star. I'm talking about Sagittarius A star, which is
okay, you're talking about the difference between the center and Sagittarius A star.
Yes.
You're talking center of rotation. So, and
you mentioned before
Sagittarius, yeah, and you mentioned before Sagittarius A star. You mentioned before Sagittarius A star is 10 to the 6 solar masses roughly, and this this center of rotation, as it were, if you like, you say you need 10 to the 12 solar masses to drive that. Is that right?
10 to 11 or 10 to the 12 to get a proper spiral structure. Yes.
Okay, and that's and you're using the center which you have defined here, which is how far did you say it was from Sagittarius A star again?
About 4.6. About 4.5 kiloparsecs, which is about 10,000 light years.
Okay, so it's a fairly significant part of the radius. Good gracious.
Yes,
okay,
it's halfway to the real center.
And are you getting that from that bulge, or are you getting that from the rotational data which you're fitting?
Well, I can't fit the rotational data for our galaxy because we don't have pictures. But I'm just guessing that it's the same as the ones we can see. All I'm saying is that they assumed that Sagittarius A star was at the center of the galaxy when they placed this beautiful satellite picture in the Mollweider section.
But it isn't.
But it isn't. It isn't.
No. Okay.
It's slightly off. So where is the sun? Well, as I said, it's out in the dark place. It's out in the dark part. We've gone way beyond the visible part of the galaxy now. If you look at a visible spiral galaxy, can I find one quickly?
So Sol will be in the dark part of any other galaxy.
So we're right out here somewhere. We're miles out. So we're in a dark part. Well, it's dark around here, isn't it? You haven't got huge light sources just very close to us. So, anyway, so that's Sagittarius A star. I said it would only take 10 minutes.